Now we're going to take a look at the ideal gas equation of state. And this is given by PV equals MRT, like this. Again, P is going to be pressure. Let's say if we're in SI units, this is usually be in kPa, and volume in meters cubed, and M is kilograms. R is going to be kilojoules over kilogram K. And finally, temperature is going to be in K, which is Kelvin. Now, R is defined to be the universal gas constant over the molecular weight. Now, some books, in fact, the book I'm using for the universal gas constant, it'll have like a R bar, and for molecular weight, they have a capital W. So you'll see it in different places in different books. And so some books, uh, you won't be given the R, but you'll have to look up uh, what the molecular weight is and divide that into the universal gas constant. And so, in general, the universal gas constant, again, RU or R bar, is given by 10.7316 psi a foot cubed. Now, this is going to be for English. And though over here I've used metric or SI units, and for SI units, 8.31447 kPa meters cubed K mole K, like this. So again, for SI units, which again we have over here, we use this. Now, some books, like the book I'm going to be using, it gives you this tabulated already. It gives you the universal gas constant divided by the molecular weight for each substance. So in that case, you don't have to actually calculate that. Now, when can you use the ideal gas equation of state? You can use it for applications that use air, hydrogen, nitrogen, oxygen, argon, helium. So these are good applications for the ideal gas law, or the ideal gas equation of state for any of these. In general, for use for high temperature, high pressure applications, excuse me, high temperature, low pressure. Do not use the ideal gas law for water, steam, um, any kind of water vapor. You could possibly use it for steam applications if you have a very, very high temperature and very, very low pressure, but I would just get in the habit of not using it at all if it has like water, steam, water vapor, etc. And for no, never use it for a liquid or any kind of mixture. Next, let's take a look at this problem. A tank contains 5 kilograms of helium at 500 kPa and 30 degrees Celsius. What is the volume of the tank? And so let's take a look at this. Now, remember, forgot to mention, I think, when we use the ideal gas law, temperatures have to be an absolute. So in this case, we're going to have our temperature in Kelvin. So we're going to have to add 273.15 to this. And we do that gives us 303.15 K, like this. And R is going to be, again, it can be either RU over molecular weight, or again, my book uses R hat over M. And now my book in the back, this value is given. In other words, you can look up in the table and find that now in mine it's table A1, you can find that this is 2.0769 kilojoules per kilogram K, like this. Now, we can apply the ideal gas law. Let's see, I guess we have everything we need. So we want PV equal MRT. And now we want to find the volume, so we'll have to solve for V. Like this. And let's start substituting. A mass is 5 kilograms. Our R was 2.0769 kilojoules. Now I'm going to convert this out. I'm going to convert the kilojoules to joules. I'm going to multiply by 1,000 to give us joules. And then the temperature is 303. And then in the denominator, we have our pressure. Again, that's 500 kPa. That's 500,000 pascals. So I'm going to convert that just to pascals, multiply that by 1,000. Like this. Now we have to check our units. Now, if you know just by looking at these how they cancel, that's fine. Let's go through just to see, like, for example, how do the joules and the pascals work out? Remember, pascals are newtons per meter squared. So we can replace that. Newton meters squared. And then remember, joules or Newton meters, like this. And let's see, be sure everything cancels properly. So again, the kelvins will cancel, the kilograms cancel, the newtons will cancel, and then we do the reciprocal, we end up with meters cubed in the numerator. So that's what we expect to have. Then when you put all this in your calculator, the volume of the tank is 6.296 meters cubed, like that. So again, it's important to be sure that your units work out properly. That's the only way to ensure you're going to get the right answer. Next, let's take a look at this example. An 8 cubic foot container contains oxygen at 120 psi. The temperature of the oxygen is 150 degrees Fahrenheit. What is the mass of the oxygen in the tank? So once again, we can look up our values in a table. In my book, my book is Kaminsky and Jensen. It's table B1. Now, again, it has the value we need right here. We don't even have to calculate it, but this time I'm going to calculate just to show you. So let's say we just had the molecular weight. So let's say if we had just a molecular weight here, which is 31.999 pounds per pound mole. I should say pound mass per pounds mole. And then if we want to find R, again, R is our RU or R hat over molecular weight. And again, uh, earlier we said that if we're in English units, this is going to be 10.7316 psi foot cubed pound mole R divided by pound mass pound mole. And again, notice the pound moles will cancel. So we, excuse me, I forgot to put the 31,999 here. And we divide this out. This becomes 0.3354 psi, psia foot cubed over pound mass Rankine. Like I said, we'll use this equation if we didn't have our R. Again, my book gives the R, so we could have just used that directly, and that would have been for oxygen. They have 3353. We calculated 3354. Pretty close. So now let's go ahead and use our equation. We want to find the mass. So again, we have PV equal MRT and solve for the mass. PV, excuse me, I'm getting messing up here. So we have this. And so let's put our values in. The pressure is 120 psi. Our volume was 8 cubic feet. Our R 3354 psi foot cubed. pound mass R, and the temperature is 150. Now we have to convert our temperature. That has to be 150 plus 460. Remember, using ideal gas laws, the temperatures always have to be an absolute. And again, let's just check our units here. The R is going to cancel. The cubic feet cancels. The PSI cancels. And then when we do the reciprocal, we'll end up with pound mass in the numerator. So that all looks right. And so the mass is, I'm getting is 4.6922 pound mass like this. Next, we're going to look at the specific heat of a substance. Again, this is defined as the amount of energy required to raise the temperature of, let's say, 1 pound mass of a substance 1 degree. Or this could also, again, that's pound mass. I don't know if my handwriting is very clear. 1 pound mass. Or you could think of it as the amount of energy required to raise the temperature of 1 kilogram of a substance 1 degree. Or you could even say grams, the amount of energy required to raise, I should write that a little bit different, to raise and in general, it's represented by C is a specific heat. And this could it be in maybe kilojoules? Again, remember, kilojoules is energy per kilogram degree Kelvin, or uh, let's say BTUs per pound mass degree Rankine. So this would be an SI units would be this way. And in English units, it would be this way. And then from this we can use this to calculate internal energy. So we looked a little bit about internal energy. We haven't really quantified it at all. And now for a solid or a liquid, we can use this for the change in internal energy. It's MC delta T. Again, for solids or liquids, like this. Now, technically, the solid must be incompressible, the solid or the liquid. So, for all practical purposes, everything that we'll be dealing with can be considered incompressible. Now, we have two types of specific heats. One is specific heat at constant pressure. And so, again, constant pressure might be represented by a case here. We have like a piston, you have like gas in here, and you have some mass up here. And you're adding heat. Again, this would be constant pressure. Like say this piston would be free to move, and you have this mass here keeping this at a specific pressure. Or again, let me just put here constant pressure. Or over here, you have the gas here. And let's say you have a rigid tank. This would be constant volume. This. So heat's added here. And so over here, you would have your CP. This is going to be specific heat. At constant pressure. And over here is CV. Specific heat. At constant volume. Now, again, because liquids and solids are generally considered incompressible, we can say for liquids and solids, CP is going to be equal to CV. And again, that's why in general, for liquids or solid, we just put like C. We don't even have a subscript because they're usually both the same. For gases, they are going to be different. And in general, when you think of this, um, if you think about, okay, what is it going to take to increase the temperature of this gas 1 degree compared to this gas? Now, think of it for a minute. When you add heat to this gas here, some of the heat is being converted to work to raise this mass up. So not all of this heat is going to go to increasing the temperature. Whereas over here, if you have a rigid tank, all the heat in effect is going to go into raising the temperature of the gas. So you're going to need less heat here than you are here. So we can say that for gases, CP is going to require more heat to raise the temperature of the gas, 1 pound of the gas, 1 degree, than it is in a constant volume case. Now, for ideal gases, we can say the change in internal energy is mCV delta T. Very similar to what we saw for liquids and solids. It's MC delta T. The only thing is we have to use the CV. It's kind of easy to remember that in the alphabet, U and V are close together. So when you're using this, use the CV. So again, this is going to be the change in internal energy for, again, this is just for an ideal gas. That this does not work for steam or vapor water mixtures. For those, see we must use the table. And we'll talk about the tables for these a little bit later.